All right, guys. This is, I think, the most important lecture. So you should stop talking to each other. And let's get started. All right, so Bayesian model comparison is, I mean, if I could say that, I would say that is the way you should use to do model selection, hypothesis testing, and it can save you from a lot of trouble when it comes to research reproducibility problems, etc., etc. You will see what I mean later on. So it is a pity that people don't use Bayesian model selection so much. There is a very good reason for that. It is extremely difficult to carry out as a process. That's why people don't use it so much. But we're coming at a point where it becomes increasingly more easier and easier to do Bayesian model selection. There are some tools out there that you can use out of the box, and maybe they work out of the box, maybe they don't, right? For some simple problems like whenever you do regression, for example, or you want to test find a correlation coefficient between a cause and an effect, they work pretty well and they are robust, these kind of approaches, and you should use them. And you will understand later on why you should use them. But let me start directly by telling you what our problem is going to be today. And the problem is as follows. You have different models, model 1, 2, 3, up to n. And as the number of the model, let's say, increases, the complexity of the model increases. Okay, so you start here with very simple models going up to very complex models. And you have some data, and the decision you have to make is what is the best model. Okay, so that's the model selection problem. And people have struggled with this question for quite a while, right? So this is Newton's answer to the problem. So we are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. Okay, makes sense. You can't quite use this thing to do model selection, but it does make sense. Here's Einstein's proposition: everything should be made as simple as possible, but not simpler. Also makes sense. Okay. But it's not usable. Okay. We'll come up with a very simple and usable proposition later. But you see, the idea is that you need to pick the simplest model that explains the data. Okay, that's the idea. Because a model that is extremely complex will explain the data, but will only explain the data you see. It will not be something that is generalizable. It is more likely for a simple model that explains the data to be applicable to different situations where you haven't seen yet. Okay. Some examples. First example I want to show you talk about is the example on the handout. Polynomial regression. So you want to do regression between an x and a y. You want to learn a function of x, and you want to do that by using polynomial expansion. Okay, and you could use polynomials of order 1. So you just do a linear regression. That's one model. Another model could be to go to second-degree polynomials, or third-degree polynomials, or even higher-degree polynomials, right? And the question is, okay, I have my x's and my y's, and I can do polynomial regression. Should I take like 100-degree polynomials, or should I take a second-degree polynomials? Where should I stop, right? Now we're going to be able to answer that. Another thing, model calibration. So imagine that you have a simple physical model, and then you have another more complex physical model, has more details, right? And then you can have a super complex physical model that has all the details. And here, of course, the more complex the model you try to use, the more assumptions you're making, right? So that's why complexity is increasing. The other thing that happens here is that the complex physical model will have more parameters, right? So even if it is wrong, it will be able to fit the data. So if you take a super complex physical model, it will fit the data better, etc. Okay? And or you could have hypothesis. And of course, hypothesis, when you want to test different hypotheses, the hypotheses are basically models of the data you have. Like what if H1? What if H2? What if H3? Etc. So how do you select between different hypotheses? And I can tell you right away how you should not select among different hypotheses. I can tell you that right now, and in case you have learned it in the past, try to unlearn it very fast. So there is this recent paper by the American Statistical Association. It's published in 2016. The paper is called basically American Statistical Association. No, that's not the name of the paper. I don't have the name of the paper actually here, but I'm sure you can find it by that. So it is a comment on the use of p-values. Do you know what p-values are? Anyone from classic statistics that you should have learned in your undergraduate? If you don't, you're very lucky actually, because if you did know about them, you will have to forget about it. Okay? So, but it is very common if you read scientific literature to see people try to do regression, for example, and then they say, oh, the null hypothesis is accepted because p is less than 0.05. Okay? And that p-value is something that arises from the frequentist approach to statistics. Now, if you don't know what it is, everything I'm going to say in the next slide is not going to make any sense to you. But if you do know what it is, then here are some of the problems with p-values that have been identified by the American Statistical Association. And let me just read you a few things. So p-values can indicate how incompatible the data are with a specified statistical model. Okay, and that's exactly what they do. But p-values do not measure the probability that the studied hypothesis is true, or the probability that the data were produced by random chance alone. And this is how people do interpret them. That's why they have to say that it is not that thing. Now, the Bayesian approach can't give you actually that very thing, that probability, and that's why it's useful. Another thing, and it's striking, is that scientific conclusions and business or policy decisions should not be based only on whether a p-value passes a specific threshold. Okay? And guess what happens in the majority of scientific literature? Conclusions are based on p-values. Proper inference requires full reporting and transparency. There are various examples where this doesn't happen. I'll give you an example later on from psychology. A p-value or statistical significance does not measure the size of an effect or the importance of a result. By itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis. So, what's the conclusion? It's completely useless. Okay, that's the conclusion. P-values should not be used. Okay, at least not on their own, not for making important decisions, not for saying I discovered something. Okay. And I don't have anything here, but I don't have a slide. But you can Google that and figure out more about it. So there's a big issue right now on reproducibility of scientific results. And there are many examples of scientific results scientific papers, peer-reviewed papers that are not reproducible. And there has been experiments out there trying to reproduce the outcomes of peer-reviewed papers. And I'll just give you some numbers from psychology, for example, which is one of the first fields that try to study the issue of reproducibility. So they did this study in 2016, I think, where they took 100 papers from their 3 best journals, okay, peer-reviewed papers, randomly picked, and they tried to reproduce them. And in all these papers, basically, the papers were of the following form. We measure this, and this thing X should affect Y, okay? Is there such an effect or not? This is the kind of papers. And it basically did simple linear regression to connect X to Y, and the question, the hypothesis they were testing with p-values was, is A, the coefficient, different than 0? That's pretty much it, okay? So we collect data, X's and Y's, and we look for that coefficient, right? So out of the 100 papers, I want to give you the correct number, which I don't remember it, all right? But I can tell you that less than 50% were reproducible. Less than 50%. I think the right number was 38% were reproducible. Actually, people managed to reproduce them. Now, these papers, they followed established scientific principles. They did their experiments correctly, they randomized X's, okay? They did the analysis using established statistical software, and they used the p-value to decide whether or not to accept the hypothesis that there is a relationship between X and Y. And they basically, all of the papers accepted the hypothesis if the p-value was less than 0.05, okay? And only 38% were reproducible. And there are many ways to understand, you know, why this thing happens. Of course, p-values should not be used to decide whether or not to test hypotheses. It should not be, really should not be used for that, especially in the regime where you have very random stuff, like in experiments with human subjects, or even nanomanufacturing is another field where you would have very random stuff, okay? So when you have very big stochasticity in your experiment, and at the same time, you cannot do thousands or millions of experiments, this is like the worst regime for p-values. This is like where they don't work. Now, to understand why these the papers were accepted for publication and all that, this is a completely different question, but I'll just give you an example. Let's say that all of us here do an experiment that has a lot of uncertainty, okay, to connect X to Y, and each one of us is going to do it just 10 times. Let's say that our experiment is we're going to throw a coin, and our hypothesis is heads is more likely, okay? So our hypothesis is that heads is like 80% likely, and the tails is 20% likely. So if all of us do it, some of us are going to see more heads, and this is they're going to think that this is an important result, and they're going to write a paper, and the paper is going to be accepted. Okay, this is exactly what happens. It may sound stupid, but that's exactly what happens. Yes.
And also that those of us that get more tails say, well, we didn't prove anything, so we won't publish it.
Exactly. Yes. So there's a bias to publish positive results. So those of us who are going to find tails, they're going to say, well, I cannot publish that. I didn't find anything. Okay, and you're going to put it on your drawer. Yes. Yes, exactly. They're going to say, the reviewers are going to say, this is all known, right? So if you go and you try, so even if you try it, if you are suspicious that this result is dubious, that tails, you know, the result that I published, for example, that heads are more possible, is dubious, and you want to get funding to test this hypothesis, you're never going to get funded because this is all known, right? Anyway, So these are problems that we have, and these problems actually will go away as we start using a Bayesian approach. So that's one thing. But perhaps even more important than Bayesian is this right here, full reporting and transparency. Okay, you report exactly everything you find, even the negative results. You report how you collected the data, how you did your analysis, so that other people can actually reproduce your analysis. Now, why is the Bayesian approach better suited for experiments with large uncertainties and low sample numbers? Is because it quantifies the epistemic uncertainty induced by these low sample numbers. So if you have a limited data set, it's going to tell you, look, you cannot really make a decision, right? So maybe you should collect more data, or maybe this thing, basically that's what you're going to get. You're going to get, well, I can't really tell you, collect more data, and then maybe I'll be able to select what is the correct hypothesis. Anyway, that's a big issue. Maybe we'll talk about it again later if I have time. And I want to prepare a little bit better for that, because this lecture is not about reproducibility, okay? It's just a side thing. All right, so Bayesian model selection, how do we do it? It's very simple, okay? It's very simple. And the key idea is this. You should put a prior over the models. You should say what you think about the models before you see any data. So you say, I have, I don't know, n models. How probable do I think its model is? And of course, if you don't know anything about the models, you should put a uniform prior over them. Okay? And that's the key idea, basically. That's pretty much it. That's everything. All right? So you have, when you're doing regression, for example, you say, well, my first model is a constant relation between x and y. So like y equals some, it is completely unrelated to x. Okay? Then my second model is y equals a times x. My third model is y equals a times x plus b x squared plus some noise. Okay? And you rank your models. So you say, I think that the first one, if you just have these three, you will say 1/3 probability for the first one, 1/3 for the second, 1/3 for the third. Okay? If you have some reasons to believe that some models are more probable than other models, then you can state that in your prior, but that's pretty much it. This is it. Put a prior on your models and then ask the question, given the data I've seen, what is the posterior distribution over the models? That's pretty much it. Okay. Okay, but there is a little bit more to the story. So you put your priors over the models, and then each model has parameters. Okay, and now we are at the regime where we were before. Before we just had a model and we had a prior on parameters. So you put a prior on the parameters. Okay, so this is your prior knowledge. And of course, before we didn't have this line. We just started directly here, and we hide. We used to hide the fact that everything depended on an assumption about a model. We didn't even show this part. We just talked about the prior of theta, ignoring that. We're actually assuming that a model is behind the scene. Okay, now we're just making explicit the model in our notation. We have the likelihood of the data, okay, which is just like the likelihood we had before. It's what we use to model the measurement process and the model discrepancy. And it's exactly the same likelihood we had before. It could be a Gaussian likelihood or any other kind of likelihood you like. But we just make M there, the model, explicit. Okay, and actually this likelihood, whether it's Gaussian or maybe it's log normal or whatever, it's part of the model, right? So your differences between models could be a difference in the measurement process, in the different assumptions about the noise as well. And once you have all that, then you can derive the posterior over parameters for a given model, right? So for a given model, you can get the posterior over the parameters. So we said that this is how you should calibrate any model whatsoever, right? Likelihood times prior is your posterior. This guy over there, We said it's the evidence, we ignored it. You can use MCMC to sample from this without knowing the denominator. But the denominator is given by basically this expression, and it just makes sure that, so it's just an integral of the numerator, okay? Ensuring that the posterior integrates to 1. That's all it does. It is this expression right here. Okay? So that's what we did so far. And of course you need to do it for model selection. But in model selection you're really interested in deriving your posterior state of knowledge or a distribution over the models themselves. So you write this, you say, what do I know about the model? What is the probability of model MI after I observe the data D? And here I just use Bayes' rule, right? So it's the likelihood of the data under the model times the prior of the model. So just Bayes' rule, okay? What is the likelihood of the data under the model? Well, this is the normalization constant. Takes a little bit of swallowing to get it, right? But it is that simple. Right? This Bayes' rule, you have a prior over models, and you have your likelihood set up and all that, and then you ask yourself the question, what do I think about the models after I see the data? Posterior, likelihood times prior. What is the likelihood of the data under a model? Well, here it is. Okay, why is it this one? What do I use here? I use the sum rule of probability. I say, well, under the likelihood under model MI is basically coming from this, okay, where I have introduced theta I, which is the parameters of the model, and I need to integrate over all the parameters using my posterior for the parameters. So this is this guy, okay? And this is pretty much it. That's all you need to do. There's only one problem, that calculating this is next to impossible. Okay, that's the only problem. And that's why people don't do it. It is possible, right? But you need to know what you're doing. Any questions? But that's the program. This is, so if you want to take one slide and apply it to your research, this is the slide. So you're doing scientific research, write down M1 is this, M2 is that, M3 is that. You have data, write down a likelihood for your measurement process. Measurement process 1 is this, measurement process 2 is this. Then calculate your posterior, calculate the evidence, do model comparison. And guess what's going to happen here? If you don't have enough data, the Bayesian approach will tell you, well, I cannot select a model. Okay? It's not going to select a model no matter what. It will tell you, look, maybe you should do more experiments. 10 experiments are not enough. Okay? Of course, if you pick a ridiculous prior, right? So if you say, I have 10 experiments, but I'm quite confident that heads is more probable, so I'm going to put in the model that says heads, probability of heads is 90%, I'm going to put probability 99%. Then guess what? Of course, you're going to see heads once, and the Bayesian approach is going to tell you your hypothesis is correct. But you're going to have to report that. And it's not going to go through peer review. Okay? Because it's a ridiculous hypothesis. Okay. Yeah.
Like this method is useful for selecting the generalized model or the model which fits best for the data we have.
So this is a consistent, if you believe that Bayesian interpretation of probabilities is correct, this is how you should update your state of knowledge about the models. This gives you the probability that a model is correct. Any model, okay? All right. Now, after you calculate these probabilities over models, you don't have to select a model, actually. Nobody forces you to select a model. unless you really have to, unless somebody really asks you to do select a model, you don't have to. You can use all the models, okay? So you can do model averaging. You can have your posteriors over the models, and then you can make predictions using each one of the models and average your predictions, okay? So you can have like a predictive distribution that averages over all the possible models, okay, by appropriate weights corresponding to the probability that each model is correct. And that's actually how we make predictions for hazards, at least hurricanes, typhoons, etc. So we have different models. We have the American model, we have the European model, we have the CNN model. I don't think anybody actually computes the evidence, but we do model averaging, okay? I don't think anybody does that because it's too expensive, but if it was possible, we should be doing it. Okay, and this thing here is the predicted distribution over a specific model, and we have seen this before, right? It involves the likelihood, and you have your parameters there, and you need to integrate over the posterior of the parameters. So these expressions, you need to spend a little bit of time with them on your specific models, on your research. Maybe going back to these slides, these are extremely generic, okay? So they apply pretty much on every single occasion. All right, and just because they are so generic, they're a little bit hard to understand just by looking at them. Okay, so you're gonna have to derive them by hand for your specific model to really appreciate what they summarize here. But it's really, you always see, what do you always see? You see an application of the sum rule, right? The sum rule of probabilities, followed by the product rule inside the summation. And then for this part here, again you have the sum rule, only now for continuous parameters, with an application of the product rule inside. So it's always the sum rule and the product rule and nothing else. Product rule is a base rule. Okay. Now if you do have to select a model, okay, of course, you can select the model that is more probable. Okay, so you can compute the posterior probability over models and say, well, I'll pick the most probable. Of course, if the most probable model has probability 55% and the other one has 45%, there is a danger that you're wrong, right? And you should be aware of that. If the probability of the best model is 99% and the other one is 1%, then okay, you can pick it, all right? Now, if you really have to pick unless you get like extreme cases of like 99% probability for a model being correct, which does happen, right? But not when you do new research, then it doesn't happen. You should not you should not decide, okay? You should not decide. But if you have to decide, then you should use a loss function to decide. You should say, how much is it going to cost me if I'm wrong? Let me minimize that cost, okay? Or you should say, what is the worst thing that can happen? Let me make sure that the worst thing that can happen is not greater than this number, okay? That's how you choose. You should take Professor Panchal's course for that, okay? But if you do choose and you want to make predictions, you can make predictions by averaging. And if somebody also forces you to pick the parameters, you should use a loss function to pick the parameters, etc. Anyway, let's go to the important thing, which is the model evidence calculation. So all this is good. There's only one thing missing, how to calculate the evidence. So let's talk about that. So this is the evidence. This is what this is the integral we need to do. And you could do it analytically if you are extremely lucky. Like, to see how lucky you should be, basically, you should be able to do the integral analytically, right? So, I don't know, Gaussian and Gaussian, it's going to give you Gaussian. Fine, then you can do it. but that's pretty much the only generic case in which it's going to work. Now the other thing you can do is you could use the Laplace approximation, and this is okay if the posterior of your model does look like a Gaussian, is sharply picked about a single point, then the Laplace approximation is going to work quite well. And I remind you the Laplace approximation, you go to the posterior and you say I want to match the posterior, fit the posterior to a Gaussian. I want to find a Gaussian that looks pretty much like my posterior. And the way you do it is, I mean, I'm doing it here, I'm repeating it for an arbitrary distribution. And what you do is you think of it like that, right? F of z and then the normalization constant. You take the logarithm of the numerator, you take its Taylor expansion around the maximum of the probability, okay? And then at that maximum, the first order term is going to be 0. And you can approximate f of z like that. And if you look a little bit more carefully, you're going to see a Gaussian. Okay, and then once you see the Gaussian here, you see the normalization constant, because it's going to be the normalization constant of the Gaussian. Okay, that's the idea. So here's the Laplace approximation for some simple examples, blah, 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 blah. But here's how it would look like. It's almost an analytic expression. The only thing that you have to find is this second derivative here, which may not be possible, right? But if it is possible, it's a good starting point. Okay, it's going to be decent, especially when your posterior is sharply picked. Then it's going to work very well. And what you see here is that you have, let's talk about it in a while. Okay, so this is how the Laplace approximation looks like. And you have the formula. Now, if you cannot do the second derivative, there is another approach. You can actually start from the Laplace approximation and say, well, I'm going to now approximate this without doing the second derivative, which amounts to basically just guessing what it is. But it's a good guess. And if you do guess in a nice way, assuming a flat prior, completely flat p of theta, p theta, and assuming full rank for the Hessian, that are the assumptions that you should make, you'll find what is known as the Bayesian information criterion. This is discussed in more detail in Bishop in the chapter where he talks about Bayesian model selection. But this is fairly simple. It tells you that it's just the log of the likelihood. The evidence is close to the log of the likelihood minus the number of dimensions that you have divided by 2 times the log of the number of samples that you have. Okay, and this is how the model evidence, the Bayesian information criterion, this approximation, crude approximation to the model evidence works for polynomial regression. And this is taken from Murphy, which is another excellent text on machine learning. And here you see Murphy trying to do regression between x and y, right? So this is the data right there. And here, and the data are actually coming from the green line, which is a quadratic function with Gaussian noise. And here he feeds a linear function. Here he feeds a two-dimensional function. Here he feeds a three-dimensional function. Three-dimensional in the sense degree 1, degree 2, degree 3. Okay, and he's doing it for 5 samples, right? So when he does it for 5 samples, look at what he finds. He finds that the more probable model is a model that is linear. Okay, the true model is quadratic, but he finds, if this is all the samples he uses, he finds that the most probable model is the linear one. But he doesn't get 0 probability for the quadratic one. Okay. Now, when he does it with more data, he does get the right answer. Okay. So what is the take-home message from this one? Is that, I mean, look at that. Even the Bayesian approach, which is the right approach, gives you here 80% probability that the actual model is linear with just 5 samples, and then 20% probability that you are wrong. You know, and we may argue, is 20% enough to neglect the hypothesis that it's a quadratic function or whatever. So if you did select the most probable model, you will be wrong. Okay. Now, depending on what exactly you're doing, you may kill people, or I don't know, have a nice publication on Nature, right? But if you have more data, then the Bayesian approach gives you a much higher probability. I mean, you see how the probability changes, right? From 5 sample points and 80% probability that you had that the first model was correct. Now, when you do 30 observations, you get almost a 98% probability that the quadratic model is the correct one. And it is the correct one. Okay? Yes?
It seems like Model 3 is better than Model 1.
Model 3 is what? This is Model 3. This is Model 1, 2, and 3.
So Model 3 seems better than Model 1.
Yeah, but it's more complicated.
So that's why it has less.
Yes, that's why it has a smaller probability of being right. So, I mean, this fit is better than this fit, but it requires 2 more parameters. And the Bayesian approach tells you, well, it doesn't really make sense to add these 2 parameters to get this much better. It's not that good anyway. I don't know what would happen if you took this out of the picture. I don't know which one it would pick then. Maybe it would flip, but I'm not sure. Actually, no, it will not flip. It will keep like that. Anyway, this is the simplest way to estimate the evidence, and it works only if you can. I mean, if you can do the Laplace approximation, you'll get a decent answer. If you cannot do the Laplace approximation, you want to use the Bayesian information criterion. This is going to be a little bit tricky because it doesn't always work, because it is based on a lot of approximations. So we learned last time, yes? It depends on the prior you have. Okay, that's a good point. So the prior we have here is basically 1/3 that each one of these models is equally probable. Okay, probability 1/3. But in reality, this model contains this model contains this model and that model. So if you wanted to be like 100% correct, you would not put equiprobable priors on them. You would put a kind of a nested prior. Like if this is correct, then this is correct for specific cases of parameters, and this is correct, then both of them are correct. And you need to come up with, I mean, whenever you have these kind of nested models, you need to think a little bit more about the prior you put. This is how it is. So here you would say, whatever probability I put to this one, the probability of this one should be equal or greater, and the difference in probability is how much I think the new, more likely, including one more parameter is. And the same thing here, and then you should solve a problem that will give you the probabilities as well. Right, but even if you completely ignore that, you would do a better job than using the p-values. So, all right. Now, we learn how to do MCMC. So you may be wondering, well, can't I use MCMC to get the model evidence? And the answer is no, you cannot, at least on its own. There is an estimator based on pure MCMC that gives you the model evidence, but it is a Monte Carlo estimator with an infinite variance. I don't know if you remember that example with an estimator with an infinite variance. So it has an infinite variance, so if you stop before infinity, you cannot trust the result. And of course that's what you would do. So you should really not use just MCMC to calculate the model evidence, because literally you can get whatever. Right? Depending on when you stop, you may get model 1 to be more probable, and if you stop later, you get model 2 to be more probable, and then if you do it a little bit more, you get model 1, so you are basically in the same regime where you can accept any hypothesis you like. Okay, so yes?
What is harmonic mean?
The harmonic mean is basically a different kind of average. We're not gonna talk about the particular estimator because it is garbage. So I'm not going to waste time explaining what it is, because it's really garbage. Okay, it is instructive, especially for a mathematician, to go and find this estimator in a paper of Neil Redford from University of Toronto, okay, and study it and see that the proof that it has infinite variance, and there is basically no estimator that is based on MCMC that has finite variance. I don't know if there is a proof that there is no approximator with MCMC period that has finite variance. I'm not aware of such a proof, but we haven't found one. Okay. Okay, so what are we going to do? Okay, that's the question. And we're going to introduce sequential Monte Carlo to go around this issue. Okay, and brace yourselves because now it's going to become complicated. Now, sequential Monte Carlo, again, my discussion of sequential Monte Carlo is going to be superficial. But you can find more details in the papers and books of Arnaud Doucet. And all the details are there, or the papers I'm going to cite later on. Okay, here's the problem, right? So our problem is to sample from this, do it efficiently, and at the same time compute the evidence. And this is actually the bigger problem. So we want to sample from a posterior, and at the same time estimate the normalization constant. If we can estimate the normalization constant, then we can do model comparison. Okay? All right, why is it difficult? Let me discuss this first. So first, MCMC takes a lot of time to converge. Okay? Another word of saying converge is thermalize. Comes from statistical physics. It has trouble with multiple modes. So if your posterior has multiple modes, I will show you in a while, MCMC will find one of them and it will stay there. It will never go to the other one. The proposal of MCMC must be handpicked. You have to pick that sigma or tune it, and it's easy to tune it for simple cases, but it's extremely complicated for higher dimensions. And the other thing that makes this integral very, very difficult to calculate is that the likelihood is most of the times sharply peaked at specific points, and it's mostly zero everywhere else. So if you sample, let's say, from the prior trying to estimate the integral, you're going to mostly get zeros. And then maybe sometimes you will fall inside the peaks, but it is very unlikely. And actually, the more data you have, the less likely it is to fall inside the peaks. I'll show you an example probability density with two peaks. So we have two peaks, this one, and they're separated by a very, very low probability region. It's not zero, but it's very low. And here's what happens with MCMC. So you start doing MCMC, and if you just look at your statistics, right? If you look at the trace of your MCMC, you will see a very, very nice trace, just exactly what you want to see. You will see an autocorrelation plot that shows completely uncorrelated samples. You will see a very nice histogram, okay? And it's very wrong, because it has only seen this peak. And it didn't jump to the other one ever, okay? So you should be a little bit careful. This is one of the problems with MCMC, and that's why you should be careful with it. If your model, if your posterior has more than one peak, it will find one of them, it will stay there, and it will look perfect. Now, theoretically speaking, if you sample for an infinite number of steps, it will go to the other one. This is guaranteed, okay? But it will never go to the other one. Now, here I use the proposal that is basically jumping a little bit, right? So to jump to the other side, it has to jump here, 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 through a series of very unlikely moves to get to the other one. Now, if I use the proposal, if I just pick the proposal so that it has moves that are very big, okay, and that's what I did here, then I can make it jump from one to the other. But the only reason that I was able to do that is because I constructed the problem, okay? The real problem, you're not going to be able to do that. So you see here a nice MCMC trace that jumps from one mode to the other mode, and you can see both modes, and the autocorrelation plot looks fine. Okay, but this is not obviously what you want to be doing, okay? Now I'll show you how the idea of sequential Monte Carlo can help you go away, cope with these problems sometimes, okay? I cannot claim that it works all the time, okay? I can only claim that it's better than MCMC. But here's the idea. The idea is to define a family of distributions that will take you from the prior, which is presumably something that you know well, to the posterior. It will take you there gradually. There are more than one ways to do that, but this is the most common way. So see here, you introduce this family of distributions that has your likelihood raised to the power of gamma, and that gamma is a number between 0 and 1. Okay, so you see it's just like your posterior, but instead of just having the likelihood there, has the likelihood to the gamma power. And depending on what gamma is, this defines a different probability density. And if gamma is 0, then you are at the prior. And it should be fairly easy to sample from the prior. It's the prior. You picked it, right? So it should be a Gaussian, an exponential distribution, whatever. It should be extremely easy to sample from here. And if you pick gamma equals 1, you get to the posterior, which is the most complex distribution you want to sample from. So now what we have managed to do is we have managed to connect the prior, which is simple, to the posterior, which is complex, through a continuous family of distributions parameterized by gamma. So for gamma equals 0, we have something very simple. For gamma equals 1, we have something very complicated. For intermediate gammas, we will have something that is a little bit complicated. Okay, and this is how it looks like in the previous example. So for gamma that is small, I get something that's close to a flat prior. Gamma 0.01, I get the yellow line. And then as I start increasing gamma, I start getting closer and closer to the original distribution. So you see that for gamma equals 0 here, it's just a flat line, okay? But for gamma equals 0.1, I get something that has modes, but they're not quite as pronounced as the modes of the posterior. And so I can still sample from that, and then as I start increasing gamma, the distributions become more complex, but they're still less complex than the full posterior. And the idea is to start samples from the simple ones and then gradually move them to the complex ones. That's the idea. All right, so the idea is to start with a particle approximation from the prior. And a particle approximation have to follow a lot of new concepts here, so this may be a little bit challenging. So the particle approximation is basically an approximation of the probability density with a bunch of delta functions. So you say basically I'm going to approximate the density with a bunch of samples that carry, each one of them carries a weight. Okay, so you start from some samples from the prior, and that should be fairly easy to construct. And then you move them a little bit. Okay, you increase gamma a little bit from gamma equals 0 to you go to gamma equals 0.01, and you move a little bit the thetas, and you move a little bit the gammas. Just the right way, in just the right way, so that the samples you get are samples from here. And then you increase gamma a little bit more, and you perturb the weights and the samples a little bit more, just the right way to get the right samples, and so on and so forth. Okay, and you do that until gamma hits 1. You will see visually how this thing works. So you start from a flat prior, the flat prior, with samples from the flat prior. Now each one of these dots here, it's a particle, and how fat it is corresponds to the weight. So the radius of the particle corresponds to the weight. And we start from gamma equals 0. What you see there up there is the inverse of gamma. And we gradually make gamma bigger and bigger and bigger until it hits 1. So you see that initially they start being uniform, and then as you increase gamma, you will see the particles concentrating on one of the two modes in just the right proportions. Okay? Yes?
How did you generate the particles?
Well, that's a $1 million question. I'm not going to tell you that. Seriously, but I will give you the code that I wrote that does that. Okay, I will give you the references, but I'm not going to tell you. I will tell you, but without the details. Okay.
How did you use the sequence to approximate?
So I will describe it. Okay, but you will not be satisfied. So I'm just telling you what's going to happen. Okay, so let's go. Let me show you another example. All right. So this is in 2 dimensions. Again, the radius of the particles is the weight of the particles, and I'm trying to sample from a distribution that has 3 modes. Okay, so these are the 3 modes. You see the contour of the distribution, and initially you start with a gamma that is 0. That has the particles distributed all over the place, and then as you increase gamma, the particles will be are attracted by the modes, and they will be captured there in just the right proportions. Okay, you can do that in as high dimensions as you like. Now, if you try to do MCMC in a space like that, you will start here, you will get captured by one of them, and then you will just stay there. You will never see the other modes. Okay, now I will tell you later how it's done. But one of the things that I want to point out about this algorithm, one of the key important factors why it's useful is that it is embarrassingly parallelizable. What do I mean by that? Each one of these guys can reside in a completely different computer or CPU. So to evolve each one of the particles, you need to go and evaluate your model, right? Because you evolve them in parallel, and there is minimal interaction between the particles. There is some interaction every once in a while to get it right, but it's minimal. It happens every once in a while. You can have each one of them on a different CPU, so you can, even though for this thing to work, the theorem says you need the number of particles to go to infinity. Okay? I mean, always something has to go to infinity. But you can have each one of the particles live in a different CPU. So if you have a high-performance computer, you can make efficient use of it, and I mean, do it at least in less time with more electricity. Okay.
So selecting 3 different particles at 3 places, can't I capture all the 3 nodes?
This is not 3 particles. It's one of these is a particle. Right? It's one of these dots is a particle. So it's one of these guys is a WI, so it has a weight and it has some parameters. Okay, and this guy has some other WJ and some other parameters. Okay? Okay, now I'll tell you how it works. I don't even think I have that. I mean, I think I have like, okay, 15 slides. Let's see where we're gonna go. Yeah, so 15 minutes. All right, so how do we do it? Consider 2 consecutive gammas, right? So gamma t and gamma t plus 1, and assume that we have a good particle approximation of the density corresponding to gamma t. And this is basically a bunch of weights and the samples corresponding to these weights. And we want to build a particle approximation for the second gamma. Okay, so we want to find another bunch of weights and another bunch of thetas. How do we do that? There are many ways, literally an infinite number of ways in which you can do it. Actually, uncountably infinite number of ways in which you can do it. I'll just give you one that I actually know it's not the best. And I'm not even going to explain how that works. Okay, I'll just tell you what it does. So we start with the particle approximation, and we want to move it to the new particle approximation. And here are the weights. I'll just tell you what it is. The weights are like that. Okay, so the new weights are basically coming from this expression where this thing right here, the capital W, is defined like this. This is the old little w, which is the normalized version of the weights. The capital ones are the unnormalized version. And here you have the ratio of the probability densities at the new gamma and the old gamma. So this is like the ratio you had in MCMC, but for 2 different distributions. Now, why is it this one? You need to read Doucet's paper to understand why it's this one. Now I'm giving you sufficient information to implement it. I'm not really telling you why it works, because to tell you why it works, it would take me 1 hour. And I do not think that anybody would follow me, except perhaps the mathematicians. Okay. So that's how you update the weights. And then to update the thetas, you need to sample from the new distribution. Now, to sample from the new distribution, you need a sampler, right? And that sampler could be your favorite MCMC. So you do need an MCMC. There is an MCMC in the background. Okay, and you use it right there. Yes?
We calculated the W gamma T plus 1, the Fourier will disappear.
What disappears?
The Fourier will calculate the W gamma T plus 1.
Are you talking about this one?
Yes, in the right side of the...
Yes, so this one is the old W. This is like this W.
Yes, in
Goes
the
there.
ratio, the Fourier will disappear.
Oh, this is not. This does not include this inside it. It's just a number that's coming from the previous step.
So the last ratio, the prior will disappear in the expression.
Well, in the
Yeah, it's the two posterior, the ratio between two posterior.
this is the ratio between two consecutive distributions, the current one and the next one you want to move. And the prior is only on the first step, and so I'll just tell you what it is at the beginning, right? So at the beginning, this you just have it because you sample somehow, and if you just sample from the prior, it's going to be 1/n. And then when you move to the second one, it will be basically 1/n, and then here you'll have this thing for the for your for your first step. Anyway, there's a lot of details. Okay, I'm very confident that that's correct because I took it for a peer-reviewed paper. That's actually math. Okay. Yes.
In the numerator, do you need a t plus 1 inside the...
No, no. You need this. You need theta gamma t, not t plus 1. You will see the algorithm completed in a while. Yes.
What are you computing here?
So what I'm computing here, I'm starting from a particle approximation of this distribution, and then I'm increasing gamma t a little bit plus 1, a little bit, and I'm giving you a particle approximation of that. So I'm telling you how you can take a particle approximation here and perturb it to get a particle approximation for the next step. Okay? Now why, and I'm telling you, this is what I do. This is what I'm telling you. I'm telling you that's what I do. I'm not telling you why it works. Okay? And I do not claim that I would tell you why it works. I do not tell you why it works.
Why do you have to do this step by step rather than do it directly?
Like go from 0 to 1.
Yes.
Because it is very hard to sample the posterior. And it is very easy to sample the prior. And if I have a particle approximation of the prior, I can very easily move it to a particle approximation that has a little bit of a positive gamma. And then I can take that and I can move it a little bit. And I can take that and I can move it a little bit until I reach the prior, the posterior. Each one of the steps is easy. The jump is hard.
So in the jump, is there any randomization?
The what?
Randomization. So do you choose the particle?
So this happens to
The particles randomly.
yes, there is a little bit of okay. So let's skip it completely. I will just say in words what happens. Okay. Once more, you start at the prior.
Yes.
You build a particle approximation there, and that's very easy to do. You just sample the prior. You give the weights. All the weights are 1/n. Okay. And then you increase gamma a little bit, and you move your particles a little bit. Now,
How do you move your particles?
that's why I was showing you, right? So the weights follow a specific formula that I show you, okay? And it's picked in just the right way, okay? It is very peculiar. It is what it is, selected specifically to achieve my goal of moving the particles. And then so the weights are changed in that way, and then the samples themselves are perturbed a little bit by doing MCMC. So I'm doing a little bit of MCMC, like 10 steps, to move them a little bit. Anyway, but the details are not important in the sense that I really have to spend 1 hour to explain why they are the way they are.
Do you move the particles randomly or move in
The particles are moved with MCMC, with Markov chain Monte Carlo. So that's random but biased with a metropolis step. Okay, so there is a metropolis step on the background.
Remove all particles at each step.
Yes. And I move them more than once. Anyway, so the thing that I want to mention, and the reason why we're doing all that, okay, is that these weights can give us an estimate of the ratio of the normalization constants between two consecutive steps. So you can show, and again, this is something that I'm not going to explain why it happens or how it happens, that the ratio between the normalization constants is the sum of the unnormalized weights of each step. It is not very hard to prove, but I'm not going to prove it. Okay? So at any given point, you can estimate this ratio. So if you can estimate these ratios, then you can estimate the normalization constant of the final step. And it's going to be the product of all the ratios. Okay? So this procedure allows you to estimate, to basically have this estimate for the normalization constant. Okay. There are a few tricks that you need to be aware of, and I'm going to talk about them in more detail next time. But one of the things that happens is that these particles, their weights, degenerate as you increase gamma. So if some of the particles, let's say, find themselves here, they're going to have a very, very, very small W, and they basically contribute nothing at the end. So what you do is you add a step that resamples the particles. It says, okay, I have particles distributed each one with different weights. Let me just resample the weight, the particles, so that the weights become 1/n again. And this is what you will see here. The particles that are very small, I don't know if you can see them, but there are some of them that are very, very, very small. Every once in a while, we throw them away. Okay? You don't have to throw them away. You can keep them around, but they're useless because they have a weight like 10 to the minus 9. Okay? So every once in a while, you say, all right, guys, freeze. Let's just reassemble. Okay? And that's called the resample step. And the resample step is based on a quantity called the effective sample size, which is basically something that tells you how, if you have a weighted particle approximation, it tells you how much information you have inside them, and that's the definition of it. And the only thing that you will have to understand for the effective sample size is that if all the weights are equal, then the effective sample size is n. It's the number of the particles, okay? So you want the weights to be as equal as possible. And if all the weight is captured, all the probability is captured by one particle, then the effective sample size is 1. So the effective sample size basically, it counts how many independent samples are contained in your particle approximation. That's what it captures. And that's what I use to do the resampling. So I'm saying, if the effective sample size drops below 50%, then do resample. The other thing that I use the effective sample size for is to select the new gamma. All right, so you can either set a fixed sequence of gammas that will take you from the prior to the posterior, or you can select that gamma adaptively. And the way I select gamma is by saying, find me the next gamma so that the effective sample size is reduced only by 5%. And this is an optimization problem that I solve to do that. Anyway, and you can see here how the different gammas are selected for some practical problems. Now the algorithm goes like that. So let me just discuss the algorithm, and then I'll tell you why you're lucky. You build an initial particle approximation from the prior. You find the next gamma so that the effective sample size is not reduced a lot. If the effective sample size is below 50% of the particles, you resample. Otherwise, You do a little bit of MCMC to perturb the samples, and you use a weight formulas to update the weights. That's pretty much it. Okay, and you're lucky because I have implemented it. Okay, that's what I like. What I like. Now, anybody who is interested in learning the details, we're gonna next time we're gonna have a tutorial on how to use this code to do model selection. This code is called PySMC on purpose because it is actually built on PyMC. So as soon as you know how to define a probabilistic model on PyMC, you can just take that model and use it with my code to do Bayesian model selection. Okay, so everything you learned last Thursday will be applicable here. So next Thursday we're gonna, this Thursday we're going to continue with that. Now, a few details about this code. So first, it used PyMC, okay? So you need to know PyMC, so please go over the handout of PyMC that we did last time before you come here on Thursday. Now, the other thing that you need to know is that this place right here is where I have written down all the details, the mathematical details about sequential Monte Carlo. So if you really want to see them, go there, okay? And all the details are there. And I have cited some of the papers where I explain where you can, how you can get the weights. And you will see that you will have to spend at least like 2 days on that to appreciate it. And of course, feel free to look at the code, okay, if you have any questions. But my goal is not to teach you how a sequential Monte Carlo works. This is not my goal. My goal is to convince you to use the model evidence in your own research, okay, and make it extremely easy for you to do so that you have absolutely no excuses for not doing so, okay? And if and I don't want you to have to go through all the details of sequential Monte Carlo to do it, okay? But you could do it on your own time later, all right? And if you send me emails bothering me, oh, I really want to see it, and this happens from more than 5 people, I will probably do it, okay? 5, more than 10, let's say 10. Because we have 7 people from math, so let's make it 10, okay? All right? Okay, so see you on Thursday. Thursday, please bring your computers. Okay, we will do model comparison with PySMC.